Here I'm going to do a torque example that's not from the book. Two children hang from their hands on a tree branch, and we know the angle of the tree branch, the weight of the two children, and how far they are along the branch. And what we'd like to find is the net torque exerted on the branch by the children. We're assuming that the axis of rotation is located where the branch joins the tree trunk and is perpendicular to the plane formed by the branch and the tree trunk. All right, so let's start our analysis. As per usual, you want to tell yourself the story and draw a picture, see if you can write down the goal and as many knowns as you can. See how far you can get in the analysis and planning on your own. All right, so here's my analysis. I started by drawing a picture. Here's the tree, here's the branch. It has this angle here above the horizontal of 27 degrees, and then it has the two children hanging from it. But then I wanted to draw it a little more abstractly, so I drew a diagram as well. So this is a little like a free body diagram, except you show the body as an extended object like that because you need to know distances to find torque, right? And the axis of rotation is where the tree hits the branch here in this picture, and here. And then the two children are represented by two forces here, and they're each pulling down with their weight, which is their mass times gravitational acceleration, right? And they're making some angle here that eventually I'm going to need to figure out. It's not 27 degrees. The 27 degrees is over here. I know they're two masses. And then my goal here is the net torque, which is the total torque, the sum of all the torques. So there's a torque from force 1 from the first kid hanging down, and there's a second torque from force 2 of the second child hanging. And my plan is to find each of those individually so that I can sum them up. And then I'm going to find them using my basic equation for torque, which is the force times the distance from the axis times sine theta. So here, I do know those two distances that are the r here. The distance of force is applied away from the axis of rotation. The first one has 1.3 meters, and the second one has 2.1 meters. So go ahead and see if you can execute this plan. All right, so torque 1 equals force 1 times the radius 1 times sine theta 1. Force 1 is just m1g, which is here 44 kilograms times 9.8 meters per second squared. So that's in newtons, right? Kilograms meters per second squared. That distance of the first child is 1.30 meters. Oh, and then the angle is a tricky thing. I need to find the angle here between the line that connects the rotational axis to our force and the force itself, right? So that's not 27 degrees, but you can kind of see these are making a triangle here, and I drew that triangle more closely here. Right, because the force points straight down, it makes a 90 degree with the horizontal here. And this 27 degrees is also with the horizontal, so it makes a nice triangle. And then I can find my missing angle because I know the three of them add up to 180 because there's 180 degrees in a triangle. So to get theta 1 up here, it's just 180 minus 27 minus 90, right? So it's 180, subtract this one, you get this one left. And in fact, you can see from this picture that theta 1 and theta 2 are the same angle. They just make two different triangles that have the same angles. Right, so then I have my sine 63 degrees, plug it all in, and I get 499.46. And if my units are newtons, because this is a newton, this is a meter, sine 63 has no units, and newton meters are the right units for a torque, so that's a good sign. Notice I'm keeping an extra couple sig figs because this is an intermediate step. I'm going to next find the second torque, the torque from the second child, and add them together. So now that you've seen me do one torque, see if you can do the second one and add them together. All right, the second one is just the same thing, except we have a different force because we have a different mass. We have a different length from the axis of rotation that force is applied. So I just plugged those numbers in. I got 641.79 newton meters. And then my goal was the sum of the two, the total torque here, which is 1,140 newton meters. Right, and I had to be careful about my sig figs because we only want 3. Now another thing you want to be careful about in torque that hasn't come up yet is I should have probably earlier chosen the sign of my torque 1 and torque 2. Now remember, the sign goes with the direction of rotation. Here, that's clockwise. Remember, and counterclockwise is our positive direction, so maybe I'll even draw that on here, right? So this would be positive. So in fact, both of our torques are negative in this case. So I would want to go in and add a minus sign here, a minus sign here, and a minus sign overall. So in fact, our torque is a negative 1,140 Newton meters because it's trying to rotate us clockwise, which is the negative direction. Now there's a little bit of ambiguity here because I drew my branch going off to the right. Now if you drew your branch going off to the left, then your two children would be trying to rotate it counterclockwise, this direction, and you would get a positive torque. So if you did that and got a positive torque, then yours is also right. It's just you started with a different picture. All right, so now I think we're done with this problem.